Uh, Hello and everyone to this week's Infosys Chandrasekharan Random Geometry Colloquium. We are here today for Hugo's second talk on rotational invariance of FT percolation. As you might have noticed from the announcement that this is twice as long, 2 hours talk. So we'll be stopping for a break, like a 5 or 10 minutes break, depending on how it goes, around 1 hour-ish time. And okay, so although I have muted everybody, but whenever you want to ask some questions, just unmute yourself and ask him. And please remember to mute yourself after that. Okay, so without further delay, to Hugo.
Well, thank you very much, Subhajit. First, I want to apologize in advance. I hope it will be for nothing, but it happened that there is an alignment of stars that made it that I cannot go to my university this week because they are moving from one building to another one. And my internet provider decided that I would have terrible internet. So my internet is probably going to be bad. I hope it's going to last, but maybe what we can do is I'm going to remove my video, and I'm encouraging everybody to remove their videos because I will not look at your faces anyway. So maybe this at least will improve a little bit, and I hope that it will hold the fort for 2 hours. Okay, so my talk is going to be a little bit different from last week. It's going to be more detailed. And also, I'm open to questions because I'm not entirely sure what is the background of everybody. So please ask questions on the chat and I will try to answer them as soon as I can. So don't let something unclear stay unclear too long, okay? So as I explained last week, the result I want to discuss is the rotation invariance of Fortuny-Castellan percolation, or I mean, I mentioned only Bernoulli percolation last week, and I will actually mostly focus on it. So let me state the result first. So statement of the result. So it's going to be a result that deals with percolation. So this I already explained a little bit what it was last week. So you have a graph. So a graph which you are going to see in our talk will be essentially always Z2 or what I call a rotated version of the rectangular lattice, which I will denote by L alpha. And I will tell you what is the precise definition in 5 minutes, say, okay? So this is just kind of a rotated version of the rectangular lattice. And for now, even for the statement, we don't need actually this. So you can forget about it, but it looks like something like that, okay? And I'm going to look at Bernoulli percolation. I mean, I'm going to look at a percolation model on it. So omega would be a function from the edges of my graph, so say Z2 or L alpha, into 0, 1. So every edge is attributed a random variable, omega e. So omega e belongs to 0, 1, and means that e is open if omega e equal 1, and otherwise it's closed if omega e equals 0. Okay, so that's, you think of omega as a subgraph of your original lattice, which has either, I mean, which has vertex set equal to the vertices of the original lattice, and edge set which is only made of the open edges. Okay, so it's a random, it's a subgraph of the original graph. Okay, and I'm going to take it at random. And typically for Bernoulli percolation, what I do is that I pick a parameter, P, which is between, and I just say that an edge E is open with probability P independently of other edges. Okay, so every edge is either open or closed. It's chosen independently for every edge, and the parameter is P of your Bernoulli or of your coin toss, if you want. Okay, and just to prepare for future notation, sometimes P will depend on the edge. So maybe, I don't know, for vertical edges of the square lattice, it's a certain P, and for horizontal edges, it's another P. Okay, but I will tell you exactly what it is. So this is just a parenthesis for now because I'm not going to use it. Now, a few things that I want you to have in mind. First thing is that we are going to always work for P. Discussed a little bit what was the critical point. It's a point that is separating between a phase where I have an infinite connected component and a phase where I don't. So for Z2, for instance, P is equal to PC and it's equal to 1/2. Okay. Okay. So we will always be at criticality. Second is that, in fact, I want to be studying the large scale properties of my model. So really, if you want, I want to be taking a huge box of size capital N, very large, and to look at big connectivity properties of my random graph omega on this big box. And you can easily imagine that it's not very convenient to take bigger and bigger boxes. So what I'm going to do is I'm going to rescale my lattice. Instead of blowing up the size of the box I'm looking, I'm going to always look at a box of fixed size, but I'm going to rescale the lattice. I'm going to shrink the lattice. Okay. So typically, I'm going to work on delta Z2, where delta is a positive parameter, but it's a positive parameter that you shouldn't think is going to tend to 0, exactly like you can think of taking n larger and larger, the size of my box to be larger and larger. Here, what I'm going to do is I'm going to take delta to be smaller and smaller. Okay. And let me mention the third thing, and this is only for a specialist, or maybe let me mention it after I state the theorem. So let me now state the theorem that I already stated last week, which is the rotation invariance of crossing probabilities. So what is it? So you fix epsilon positive. Then there exists a delta 0, which depends on epsilon, such that for any delta smaller than delta 0, for any quad, I'm going to tell you a little bit what this is. And this quad, I want it to be non-degenerated. I'm going to also tell you a little bit what this is, but I'm going to ask that its extremal length is between epsilon and 1/epsilon. So if I take all of that, then if I compare the probability, oh, by the way, the measure, I'm going to denote it. So here, let me write it in green. So the measure, I'm going to denote it phi. And I'm going to put here the graph, so say delta Z2, for instance, or delta L of alpha. But I'm not going to remind you of the parameter P because it's always the critical one. Okay, so really keep that in mind. It's always a critical parameter. So I drop P as a parameter from the definition of my measure. Okay. And so what I want is I want to be looking at a crossing probability in two graphs. The first one, so I look at my quad. This is a Q. So I'm going to try to repeat it, but I mean, obviously, I'm not so good at this. Okay, let's say it's like that. I look at the crossing probability, so the existence of an open path from AB to CD, okay? But I look at it on two different graphs. The first graph is delta Z2, but the second graph, and maybe I should be a little bit more careful, let me put it like that, is also delta Z2, but rotated by an angle e to the I theta. So I'm also going to add here for every theta in R. So in some sense, I'm rotating the lattice, which you can think of as rotating the quad if you prefer to stay on the square lattice. And what it says is that this is smaller than epsilon, okay? Okay, so just a few comments, maybe very brief comments on this theorem. And then, of course, I will try to tell you actually to state an even better theorem. So first thing I want to advertise is what is this thing? What does this mean, this? Why do I put this? So for people who don't know, let me remind you maybe here, what is the extremal length of a topological quad? So a topological quad is really what you think it is, meaning it's something that looks like a rectangle, okay? Meaning it's a domain in the plane with 4 points, 4 marked points on the boundary, okay? And the extremal length of this domain is the following quantity. I mean, since it is a simply connected domain in the plane, it can be mapped to a rectangle. And if you think about it, if you want the 4 points, the 4 marked points to be sent to the 4 marked points, I mean, to the 4 corners of the rectangle, and if you want, say, the height of your rectangle to be 1, then for any topological quad, there is a unique length here, L, for which this is possible. Okay, so if you want, so this, I mean, this L is determined by my original domain. Well, this L is exactly what we call, oh, sorry, not what I meant. It's exactly what we call the extremal length of my domain. In some sense, it's measuring how thin your topological quad is, okay? So here, I'm asking that the quad has a topology, has an extremal distance, which is extremal length, which is between epsilon and 1 over epsilon. And the reason is that you can easily believe that if I allow myself extremely thin quads, you know, something that would look like that, for instance, maybe with a spacing of delta here, then it's very degenerated. Even the probabilities are probably very small or very close to 1. So things go wrong when you allow yourself arbitrary quads. But this constraint here is kind of, I mean, asking that the extremal distance is between epsilon and 1 over epsilon is just a way to control, if you want, that the quad is not too degenerated. So it's not really a constraint, if you want. It's just a natural assumption, okay? That's the first thing. So the second thing, and this is really the important thing, is that I'm asking that this is true for every rotation. Yeah, Sébastien, in a quad, should the boundary avoid infinity? Can we take stuff such as a disk minus a radius? A disk minus a radius. What do you mean by this? Where two sides of the quad turn out to be at, yes, so two sides of the quad can be at the same place. You really think of allowed, no
Sorry.
problem with that. And
Sorry.
say here, if yes,
Sorry,
if you have
Hugo.
A and B, you think of this as being there. Yes?
We lost actually, I think, for a while. So when you started the answer. So
Ah,
could you please repeat? Yeah.
okay. When I started the answer, okay. So there is no problem with having a segment that is corresponding, if you want, to two sides of your quad. You can take a disk minus a path, for instance. It's just that then you need to think of points along this path that you removed as prime ends. If you want, you have 2 points, one on each side of your path. Here, these points correspond to two. I mean, let me redo maybe the drawing a little bit bigger. So let's say you are taking something like that. At every point like that, you have 2 prime ends. You have one on this side and one on this side. It's a very classical notion of conformal analysis and I mean holomorphic maps and so on. There is no problem with that, and it works perfectly for our theorem. This is perfectly allowed. Yes. Infinity would be a little bit more complicated, but we can still do it. Yes, actually, maybe we even did add something in the paper. Okay, let me finish this first slide by mentioning something that I'm only going to mention here and not later, but that I want at least specialists to keep in mind. Okay, so the second thing I want to keep you in mind is that, in fact, the theorem generalizes to all FK percolation model, all the Fortuyn-Castellan percolation. So Bernoulli percolation is only one example of a large class of percolation models. And in this large class, there is a bunch of these models that satisfy that undergo what we call a continuous phase transition. And for this model, we can extend the theorem. More precisely, for those who know, we can extend the theorem for Q between 1 and 4 for the FK percolation. If you never heard about Fortuyn-Castellan percolation or random cluster model, which is another name for that, ignore this green comment. It's not so important for you and stick with Bernoulli percolation, but I just wanted to mention that it extends to all this Fortuyn-Castellan percolation and that this is maybe one of the most interesting aspects of the theorem, that it is actually fairly robust. Okay, but I'm going to try to simplify as much as possible, and already you are going to see it's not that simple. So I'm going to ignore this generalization to FK percolation and focus on the Bernoulli percolation. Okay. Are there questions on this first theorem? Maybe is it clear enough, or do we need that Q is larger than delta in size in the theorem? Yes, actually, you are entirely right. And now that I see the theorem as it is stated is not really valid, you are right. And actually, it's very interesting because this is also the case in the paper. So you need indeed a minimal size for Q. Yes. So maybe you want also Q maybe to have. So how will I write it? That's a very, very good point, Misha. So maybe the distance between AB and CD should also be larger than epsilon. Yes, yes, you are entirely right. Thank you. Of course, I mean, what Misha is noticing, and which is very true, is that if you shrink a quad, it doesn't change its extremal length. So obviously, you know, the more, I mean, if you shrink the quad to a size delta, then basically, if you rescale everything, you are on the square lattice with mesh size 1 when you look at it. No, it's an important remark, Misha. Thank you very much. So you want to think really of a quad of given size, like really in the plane, and then you shrink the lattice. Okay, very, very good. Thank you, Misha. That's a very good comment. Okay, so I'm adding this. Okay, so let me give now a new theorem, a new way of writing the theorem, which doesn't involve extremal distance, which for some people I'm pretty sure you will be happy about, and which is actually giving something stronger than what I stated. So the second theorem, let's call it theorem 2. Let's say this was theorem 1. Up. So theorem 2, I'm going to call it full rotation invariance. And it stated the following. So you still stay with Bernoulli percolation, but for those who know, you can also extend to Fortune-Castellane. So you fix epsilon as before, and I claim that there exists a delta 0 as before, such that, again, for any delta smaller than delta 0, for any theta, there exists, and that's where things are going to change, there exists a coupling. I'm going to call it P, but I want you to remember that it actually depends on epsilon, delta, and theta between two things, between omega delta, which is sampled according to phi delta Z2, and omega prime delta sampled as the same thing. So you take two copies of a Bernoulli percolation on delta Z2. And this coupling, P, I want it. So this is what? I want it to have the following property. I want that the probability that the distance between omega delta and e to the I theta omega delta prime, the probability that this distance is larger than epsilon is smaller than epsilon. And here I want, and I'm going to tell you more details about it, I want this distance to be in some sense measuring how close omega delta and e to the I theta omega prime delta are. And there are two kind of, let's say, classical, maybe this is not an ideal word, but there are two classical distances to measure the distance between two, if you want, random percolation configuration. And these distances are called, or I'm gonna call them like that. It can be the Kamiya Newman distance, or it can be the Schramm-Smirnov distance. So at this stage, don't worry if you never heard about these distances. It's not such a big deal as long as you are not in percolation theory. If you are in percolation theory, worry a little bit because you should have heard about these distances. And I encourage you to try to take a look at what they are. But let me tell you a little bit about the Kamian-Newman distance, okay? Because this is one distance, at least I can explain a little bit. The Schramm, there are two M's, obviously. The Schramm-Smirnov distance is not so easy to define, and maybe I'm just going to ignore it and just focus on the Kamian-Newman. So remember last week, I briefly mentioned that, discuss how one can see a big Bernoulli, a big percolation configuration. And I mentioned there are several ways. Maybe you want to be determining which area is connected to which area. Maybe you want to be thinking of large clusters. So here, what I want to be using to define the Kamian-Newman distance is I want to be thinking of a big percolation configuration as a collection of non-intersecting loops, non-crossing loops. So what do I do by that? Imagine I'm going to make just one drawing first. And imagine that, so this is the square lattice, the big one, by the way. And imagine that I have a Bernoulli percolation picture. Okay, so these are the open edges in a
Hugo,
Bernoulli percolation. Yes?
we lost you from when you started saying Bernoulli at the first time. Yeah, but
Oh, Bernoulli. I said Bernoulli at the very beginning of my talk. So this is a very. And did I
right now,
start
right now, right
drawing
now.
or not?
Yeah, yeah. Just after you started the
Okay.
drawing. Yeah, yeah.
Yes, I'm really sorry about this. If you want to hate French even more than you already do, just think that the internet providers in France are trying to ruin our lives. Anyway, so what is that? So now it's not only internet; it's also Apple. Okay, good. So this imagine is percolation configuration. The bold edges are the open edges. So what I can do is I can draw a dual lattice to the square lattice by putting a vertex in the middle of every face of the square lattice. Okay, so let me. And now I can decide that an edge of the dual lattice. So I mean, the lattice is obviously, you can guess that you are just reproducing, you are connecting edges that are neighboring each other. Actually, I'm making a horrible drawing, sorry. And now what I'm going to do is I'm going to define a dual configuration of the original configuration, where I'm going to open an edge of the dual lattice if and only if the primal edge, the corresponding edge of the original lattice, is closed. Okay? So I end up with, if you want, filling up the gaps like that in the dual lattice. Okay? So this is a configuration. So if you start from omega, I notice that I configuration omega, you end up with a configuration omega star, which is called the dual configuration. Once you have drawn, like I did, the primal and dual configurations, there is a very cute way to drawing loops. What you do is that you kind of surround, I mean, you just go around the primal clusters without crossing the dual ones and vice versa. So you just wind around like that between the clusters of the primal and dual configuration. Okay, let me stop here for the drawing. And what you end up is with a collection of loops. So from these two, if you want, by taking them together, you can end up with a configuration that I'm going to denote like that, which is a configuration of loops. The loops are the boundaries between the primal and the dual clusters, or if you want to just forget about the dual clusters, it's just a natural way of drawing the boundaries of the primal clusters. Okay, just think of that, the clusters of omega. Is this drawing kind of clear or not? I mean, I can do much, I mean, can discuss much more this thing, but you can also just trust me that there is a kind of natural way of drawing loops that surround the clusters, I mean, that go along the boundaries of the clusters. So the result of this is that, yes, you can think of Bernoulli percolation configuration as just a subgraph of Z2, but you can also think of it as a collection of loops. These loops, if you think about it, they cannot, I mean, they are self-avoiding if you want, okay? So now, what is the distance, the Kamian-Newman distance? Well, let's first try to see what is the distance between two loops. So imagine I have one loop and a second loop like that. You agree that here, is it necessary all loops are closed? This is a good question. So you remember I mentioned last week, I mean, you probably remind you now that I mentioned last week that there is no infinite cluster. So as a consequence, all loops are closed. In fact, even when there is an infinite cluster, if you know a little bit about Bernoulli percolation, the dual configuration will not have an infinite cluster. It cannot be that the primal and dual configurations both have an infinite cluster. So it's impossible that you have an infinite loop, an infinite path. All loops are going to be closed. It's necessary at any p, in fact. So it's a good question, and this is the answer. Hope it helps. Okay, so when you look at these two, this black and this green configurations, you will agree with me that you kind of feel like these two configurations are close to each other. So I'm going to, these two maps, these two loops, sorry. So there is a loop gamma and there is a loop gamma prime. So I'm going to set that the distance between two loops, so let me write it here. The distance between gamma and gamma prime is the infimum, and I'm going to tell you what this infimum is, of the supremum over T in S1, in the circle of length 1, of gamma of T minus gamma prime of T. So what is this infimum? This infimum is just the infimum over any parametrizations of gamma and gamma prime. Over parametrization by S1. So one-to-one parametrization by S1 and continuous parametrization. So what does it mean? I'm going to say that gamma and gamma prime are within distance epsilon of each other if I can find a parametrization of gamma and a parametrization of gamma prime in such a way that at every time t, gamma of t minus gamma prime of t is smaller than epsilon. It's a Gromov-Hausdorff distance, basically. And then from that, between two configurations, omega and omega prime. So I think of, so the Kamian Newman distance between omega and omega prime, when seen as collection, it's only if for every gamma in omega, in omega, there exists gamma prime in omega prime such that the distance between gamma and gamma prime is smaller than epsilon, and vice versa, meaning for any gamma prime in omega bar prime, there exists a gamma in omega bar such that the distance between gamma and gamma prime is smaller than epsilon. Okay, it's to have the symmetry of the distance that you do this. So basically, the Kamian Newman distance, which I did not like that. You notice that I introduce a notation without telling you what this is. So this is a Kamian. So you could have here Cn for Kamian Newman. Is basically saying all loops, you can find another loop in the other configuration, which is close to the original loop. Notice one thing is that this is almost trivial for any loop which has a small radius. Because if you take a loop in omega bar, which has radius smaller than epsilon, say, in some sense, you only need to find another loop in omega bar prime, which has radius smaller than epsilon and is close to the original loop. It's almost, you almost only need that. And this comes for free, basically. So the Kamian-Newman distance is really going to be larger than epsilon if a big loop is kind of alone. That, I mean, in the other configuration, you cannot find a big loop which is close to it. So the Kamian-Newman distance, really think of it as large distance. Okay, very good. Are there questions on this Kamian-Newman distance? Or can you believe that this is kind of a natural distance to control what happens? Sébastien, do you ask this for all loops or all loops in the ball of center? Yeah, okay, right, Sébastien. Maybe, I mean, I have always in mind the finite volume thing, but here I forgot. So so for any loop, I'm going to write it like that. Indeed, you need to control a little bit, so such that gamma is included in the ball of size 1 over epsilon. There exists gamma prime in omega bar prime such that distance between gamma prime is smaller than epsilon. Very good. Yes, you're entirely right. Let's restrict ourselves to a finite volume. Okay. Are there other questions on, I mean, all these questions are very good because it's, I mean, basically I forget to mention a few assumptions. Are there other questions? If not, let me tell you a little bit about the applications of this. So maybe it's a second point. Applications. Okay, so the first item is that theorem 2.
Wait, sorry, can I just ask? So
yes.
is it? So I think I kind of see why theorem 2 implies theorem 1. And is it true that you get this lower bound on the extremal length because of this this less than epsilon in the distance?
Yes, exactly. I mean, okay, I should say, in fact, these lower bound and upper bounds on extremal lengths are a little bit useless because for quads that have a terrible extremal length, you can actually trivially, you see, if the extremal length is very small, so the distance between the 2 points, the 2 arcs is very small, you can basically say that in both cases, the probability is very close to 1. And on the contrary, if it's very large extremal length, extremal distance, then both probabilities are close to 0. So you see, it's typically what you realize when you start presenting the papers, right? I mean, I think we all had this experience that we state a theorem, which for us is the right way of stating the theorem. But once you start presenting the papers, you realize that, oh, maybe there is a better statement. So here, I think this extremal length is not really necessary if you just say that in any case, both quantities are very close to epsilon if the extremal distance is large. So both are very close to epsilon if the extremal distance is large. And both are very, so in fact, this extremal length is not so important. The distance assumption that Misha reminded me of, this is important because indeed, this is where you are going to use really the Kamian Newman distance as you control. I mean, you only control the large loops, so you want basically to be looking at crossing probability of large clusters. Okay. So theorem 2 indeed implies theorem 1 because it's not very difficult to convince yourself that if you know that big loops are close to each other, then crossing, I mean, you have a crossing of a quad if and only if you have, I mean, in one configuration, if only if you have it in the other one. So this is easy in some sense. Okay. Second thing, which is maybe less easy, but still a little bit, I'm losing a lot of, just give me 1 second because I'm almost without battery anymore. Give me 1 second. Okay, I'm back and I'm not going to lose you. I mean, it's unbelievable how fast my battery is decreasing. Okay, so second property, which is much less clear, but it's still true, is that at least in physics, there is a natural quantity you want to be studying, is you want to be studying correlations between points, basically. And in Bernoulli percolation, the natural quantity would be the following. You take 2 points, x and y, and you look at whether they are connected. So this is just a notation to say connected by an open path. So here you see you are taking 2 points really off your lattice, and you try to look whether you have connection between the 2 points. And this, you could still, I mean, you could start to be worried that maybe, so when delta tends to 0, so this is a little of 1 that has to be interpreted as tending to 0 as delta tends to 0. It should be very close to the same quantity for e to the I theta x and e to the I theta y. Right? I mean, if you think of rotation invariance, you want to be saying that picking 2 points or picking rotations of these points, you should have the same connectivity probability. But notice that it's a little bit tedious because these connectivity probabilities, they don't only involve what is happening far, I mean, at large scales, right? I mean, think of it at the very, when you reach, say, the ball of size 10 delta around x and the ball of size 10 delta around y, where there, now, in some sense, if you rescale, you are looking really at a box of size 10 on the lattice. So it's very scary because this is not rotation invariant, but still you have coupling techniques that allow you to prove that still, in some sense, even if nearby each variant, probabilities are rotation invariance as a whole. In some sense, there is kind of a cancelling effect, and you end up with something which is rotation invariant. Okay, so you can really, correlation functions in the model are still rotation invariant. And by the way, if you and you want, for instance, that the 8th point is connected to the 7th, but to nobody else, maybe all the others are connected, you ask for the probability of this rotationally invariant. Like any type of connectivity probabilities between points is rotationally invariant. So this is a very cool corollary. In particular, because, and this is the only place where I'm going to tell you a little bit about other models. You remember I told you that these things were true for Fortuyn-Castellane percolation. One of the advantages of the Fortuyn-Castellane percolation is that it's related to the Potts model. If you don't know what a Potts model or FK percolation is, ignore what I'm going to be saying here. It's not very important, but at least maybe it's going to give you a vibe that this theorem has application. So FK percolation is connected to the Potts model. And here I told you when Q is between 1 and 4 is the result. The result is working for this Q. So it's going to correspond for the Potts model with 2, 3, or 4 colors. And what you end up here is you end up with rotation invariance of spin-spin correlation in the Potts model. And this is really coming from, I mean, for people who know, it's item 2 plus the Edwards-Sokal coupling. And that's also why it's interesting to get item 2. If you don't know about this, ignore it. It's not important, and it's really just an example of an application. This is going to be even more true for the next application, which is the rotation invariance of the 6-vertex height function. So this is even more true. If you don't know what this is, ignore it. And here you get rotation invariance of the height function for delta between -1 and -1/2. This item 3 and 4, I didn't want you to, if you never heard about these models, it makes no sense for you. But what you can at least believe me is that the rotation invariance of this Fortune-Castellan percolation in the models. That's what I wanted you to kind of understand and keep in mind. Okay, so you get rotation invariant of many other models by proving rotation invariance of Fortune-Castellan percolation. It's kind of a master model, if you want, that is implying which is implying rotation invariance of many other models. Okay, that was kind of a parenthesis about the applications. Now, let me tell you a little bit more about how you get this rotation invariance. And the first thing I'm going to do, and this is going to be the end of this part of the talk, of the first half, is that I'm going to restate the theorem in a different fashion. In fact, this rotation invariance is going to come from a universality result, what we call. So rotation invariance from universality. Don't worry, I'm going to tell you what universality means. So the idea is not actually to try to directly couple a configuration on the square lattice with a configuration on a rotated version of the square lattice. Our idea is that we are going to couple Bernoulli percolation on the square lattice percolation on different, what we call isoradial graphs with isoradial weights. And here, in fact, it's going to be very specific isoradial graph and weight. So I'm not going to, so it's going to be very simple. So I'm not going to tell you what an isoradial graph is. I'm just going to example of the graph itself. So I'm going to couple omega delta, which is, as we said, defined on delta Z2, with omega prime delta, which is defined on delta L alpha. And from now on, Z2, I'm going to call it L pi over 2. You're going to understand in a second why. So what are these graphs? So here I have an angle of pi over 2. And what I did is that the original lattice, but rotated by an angle of pi over 2. Okay. And what I did is, if you remember the notion of dual graph that I defined before, what I did is that I drew the vertices of the dual graph, and I connected the vertices of the dual graph to the vertices of the primal graph to get a black lattice, which is a square lattice rescaled, if you want, by a square root 2 over 2. Okay? Is it clear how you define this black lattice from the green lattice? Okay, so now imagine, so this is nice because you have small squares as faces. Now imagine you do the same, but instead of small squares, you define lozenges with an angle alpha like that. So again, if you want here, it's square with mesh size 1, or maybe square root 2 over 2, but I mean, think of mesh size 1. Of side 1, but with an angle alpha. Okay, so draw them like that, as I did, and now do the reverse procedure to the process that led from the green to the black lattice. So if you do it, what you end up with is you end up with a rotated version of the square lattice, of the rectangular lattice. Okay, you see here now, I have an original green lattice, and I have, if you want, a dual lattice with gray edges. This is not good. This is here. I mean, my drawing is not ideal, but with gray vertices in the middle of the face. Okay, so you end up with a lattice like that, which I'm going to call L alpha. Okay, so here I have the square lattice, which I call L pi over 2. So pi over 2 or alpha is just the angle of these small lozenges. And here I have L of alpha. So I want to be coupling omega on the original lattice to omega prime on this kind of rotated version of the okay. And the theorem, and this is our third theorem, is saying the following: its universality along, or among isoradial rectangular graph. And it says the following: it says that there exists a coupling. So for any epsilon, there exists a delta 0 of epsilon, such that for any, theta became alpha, but for any alpha in R, for any delta smaller than delta 0 of epsilon, there exists a coupling P that again depends on delta, alpha, and epsilon, such that the probability of having distance, or coupling like phi delta L of pi over 2, and omega prime delta like theta phi of delta L of alpha, such that the probability that the distance between omega delta and omega prime delta, let's say the Kamian Newman distance, is smaller than epsilon. Okay. Okay. So you see, it's exactly the same statement as before. Exactly. The only difference compared to this theorem is that we are not coupling the same thing. Here we are coupling omega delta, which is on delta times, not the square lattice, but really a rotation by pi over 4 of the square lattice, and omega prime delta, which is on delta L alpha. Okay? So just we don't couple the same thing, but otherwise it's the same statement. So in particular, it's called a universality result, large-scale properties of the Bernoulli percolation on the square lattice or on the rectangular lattice, but rotated by an angle alpha, are the same. Okay, that's called universality. So just before I stop this first half, in 1 minute or 2, let me tell you why this is implying the original theorem. Trish, can you motivate a little why we work on the green graph? Not sure if you said it, but cut out. I don't immediately see the gain in working on them as opposed to black. Let me answer that. Okay, I can answer that now. So you can ignore the black lattice. Just ignore it. Just think green lattice, okay? It's just that in order to construct the green lattice, I went through the black lattice. The black lattice is going to be involved later on, but for now, ignore the black lattice, okay? So just work on the green one. So there is no even motivation, just think, forget this here, and just think, okay, I have 2 lattices, and I'm comparing Bernoulli percolation on these lattices. Okay. Just to conclude here, it doesn't seem I'm proving anything related to my original question, except that imagine you take omega delta sample according to phi delta Z2, delta L of pi over 2. So you agree that this has the same law as sigma 0 omega delta, which is sigma 0 is just a reflection with respect to the vertical line, right? The vertical line, the horizontal line. The horizontal line is a symmetry of the lattice L pi over 2, right? If I take this thing, it's a symmetry of the lattice pi over 2, L pi over 2. So, I mean, the law of omega delta or sigma 0 omega delta is the same. Okay? But notice that this guy, oh, sorry, where I am. This guy has the same, I mean, is approximately in law equal to sigma 0 of omega prime delta. Okay? Why? Because this is a theorem which is telling us that, like the distance, the Kamiya, I mean, I can couple in such a way that the Kamiya Newman distance is very close for omega delta and omega prime delta. So now this guy is on the reflection of the rectangular lattice. But omega prime delta itself has the same law as sigma alpha. So sigma 0 is maybe I mentioned it, maybe I didn't. So sigma 0 is a reflection with respect to the horizontal line. So sigma alpha is going to be the reflection with respect to this line here. And you see that this is a reflection which is preserving the lattice L alpha. So omega prime delta has the same law as sigma alpha of omega prime delta. Okay? But omega prime delta again has almost the same law by applying again the theorem as omega double prime of delta, which is on phi delta L pi over 2, right? Because omega prime delta is on the right lattice. I can apply again the theorem to go back to my original lattice. So what I got is that I have a chain of connections, of relations between omega delta, which is sampled on delta times L pi over 2, and omega double prime delta, which is sampled on delta L pi over 2. But the good thing about this relation is that it's not a relation between omega delta and omega double prime of delta. It's a relation between omega delta and the image under sigma 0 sigma alpha of omega double prime of delta. But the image, I mean, sigma 0 sigma alpha is just e to the 2I alpha. It's a rotation by an angle alpha. Okay. So what I just proved is that omega delta on delta L pi over 2 is very close to the rotation by 2 alpha of a configuration, not an independent one, but a configuration on phi delta L pi over 2 again. This is exactly what I wanted for theta equal 2 alpha. So this gives the result for theta equal 2 alpha. Okay, so if I can prove universality among isorectangular rectangular graphs, I will get, by this chain of relations, rotation invariance for the original graph. Okay, so I suggest that we make a break, a 10-minute break now, 2 or 5 minutes, I don't know. I mean, I'm not the organizer, so budget, you should choose which you prefer. And then what I would start to do is tell you a little bit about the proof, but I mean, of course, I'm not going to give you the whole argument, but try to give you at least the roadmap of the proof of this universality. Okay.
Okay.
Subhajit?
Yes.
do you
So
agree?
let us reconvent. Yeah, in 5 minutes.
Perfect.